Section 4, the completeness axiom. Okay, so so like I said, this is the property that distinguishes R from Q. Okay, this is what makes R R. Okay, and so we start off with a simple idea, the notion of the maximum. Okay, so you have a set in R, and S is not the empty set. If there exists some element contained in the set such that that element is bigger than or equal to anybody else in the set, then we say that S has a maximum. S has a maximum, namely that S naught, and we write S naught equals the max of S. S naught is the max of S. Okay. And similarly, for minimum. Okay, so right, if you have some number that is bigger than, if there's some number in the set, okay, and that number is bigger than everybody else, then we say that S has a maximum. Okay, so for example, so notice that number has to be in the set. It's not outside of the set. Okay.
What does the VIZ in parentheses mean?
Namely.
Oh, thank you.
It's a Latin abbreviation. Yeah. So okay. So for example, any finite non-empty set in R has a maximum and a minimum. Any finite non-empty set in R has a maximum and a minimum. Okay, and that's sort of obvious, right? If you have a finite number of elements, then there's going to be some biggest one, right? And that one will be the maximum. Or there's going to be some smallest one, and that one will be the maximum. Okay, but of course in mathematics we can't just say it's obvious, so you have to prove it. Okay, so I'm going to have you prove it for the homework. Okay, you can do proof. You can do it by induction, or some other way you feel like. Okay. Okay. What if the set is infinite? What if the set is infinite? Does it have to have a maximum? Can somebody give me an example of a set without a maximum, or a set without a minimum, or a set without a maximum or minimum? E to the x? Okay, so maybe you're saying like e to the x where x ranges over the reals, right? Like all outputs of e to the x, right? That'd be good because there's no maximum for that, right? No matter what, right? If you tell me that e to the x naught is the maximum, I'd say, well, e to the x naught plus 1 is bigger than that, right? So you can't find somebody who's a maximum, right? There's no element of the range of this function that's a maximum. Of course, you see that in the picture as well, right? So looks something like this. The graph looks like this, right? No output is highest, and no output is smallest either, right? There's no smallest element. Okay. 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 So this is a very simple idea, maximum and minimum. Okay. Now, a slightly more, I don't know, maybe this is more sophisticated or equally simplistic. So there's another notion. Suppose you have a set in R, and again, R is not the empty set. If there exists an element in R such that that element is bigger than everybody in S, then we say S is bounded above. Bounded above. And call M an upper bound of S. Call M an upper bound of S. Okay. And similarly, for bounded below and lower bound. Okay. So, for example, this set here that Jacqueline gave, right, is what? Using this language.
Has no upper bound?
It has no upper bound, right? It's not bounded above, but
Bounded below.
it's bounded below, right? By 0. Yeah, by 0. Right? Because as x goes to negative infinity, u of the x shrinks down, gets arbitrarily close to 0. Okay. So this set doesn't have a max or a min, but we do have, and it has no upper bounds, but it has lower bounds, right? So 0 is a lower bound. Negative 1 is also a lower bound, right? You can take anything smaller than 0. All those guys are going to be lower bounds. Okay. 3, if S is bounded above and below, we call it bounded. We call it a bounded set. Okay, so yeah, so one example, if we look at the set 0, 1, well, that has upper bounds, it has lower bounds, it's a bounded set, right? Does it have a maximum?
No. It doesn't, because 9 isn't part of the set.
Right, so that's the trick, right? It doesn't have a maximum. Because the maximum has to be in the set.
And one's not in the set.
One's not in the set, right? This is the open interval 0, 1, so one's not in the set. So so if it's like this, then it does have a maximum. 1 is the maximum, 0 is the minimum. Okay, but this one doesn't have a max, it doesn't have a minimum. Okay. Okay, so now we get to the critical definition. The critical definition, here it is. Again, let S be a subset of R and S not be the empty set. If there exists an upper bound M naught of S with the property that M naught is less than or equal to M for all upper bounds M of S, then we call this M naught the least upper bound of S. Okay. And we denote it the least upper bound of S, or sometimes it's called the supremum of S. Supremum. The supremum of S. Okay, so by looking at looking at the set 0, 1, right? Looking at the set 0, 1 that we had earlier, right? 1 is the least upper bound, right? 1 is the least upper bound of the set, right? 1 is the least upper bound of the set of 0, 1, right? Because, right? If you have any other upper bound, well, 1 is going to be less than or equal to that other upper bound, right? Anybody who bounds this set is either going to be 1 or bigger than 1. Okay, so this 1 is the least upper bound. And similarly, we have the notion of the greatest lower bound. Okay, so similarly, we have the greatest lower bound, which is called the infimum. The infimum. Okay. And now, let's state the property that distinguishes R. So the completeness axiom also called the least upper bound axiom. Okay, here it is. Again, you have a subset of R that is non-empty. If S has an upper bound, then it has a least upper bound. In R. Okay. So any non-empty set that has an upper bound has a least upper bound. Any non-empty set with an upper bound has a least upper bound. Okay. And so this is not a theorem. You notice this isn't a theorem. We don't have to prove it. Okay. We don't prove it. This is part of how you construct R. Okay. So this is part of the construction of R. Right. You basically make R to be a field that contains the rational numbers and has the least upper bound property. That's what R is. So you don't have to prove it. That's when you build R. That's what R is. Okay. Those of you who want to see the construction, if you look in Rudin's Principles of Real Analysis, in the appendix to Chapter 1, they give the construction of the real numbers. Okay. But it's kind of complicated, I think. Okay. So let me just say one thing. So this is the property that R has that Q doesn't have, and if you consider, so if you notice that Q, if we consider the set of rational numbers. So suppose we're in Q, the rational numbers, and we consider the guys whose square is less than 2. Okay, the guys whose square is less than 2. Okay, so 0, 0, you have some set of numbers, the square is less than 2. Okay, so this has an upper bound, right? Like if I take 2 is here. Everybody, all these guys are, between -2 and 2. This is a bounded set, right? It has an upper bound, but there is no least upper bound in Q. Okay. If we're in R, there is a least upper bound, right? The least upper bound is the square root of 2, right? The greatest lower bound is negative the square root of 2, right? But those numbers don't exist in Q, right? And so in Q, there's just this hole there, right? So there's no, you can find least upper bounds, right? But 1.5, that's the least upper bound, 1.42, I'm sorry, that's 1.5 is an upper bound, 1.42, that's an upper bound. These are all rational upper bounds, but they're not the least upper bound. And in fact, we can't get a least upper bound if we stick with the rational numbers. Okay, that's it for today. Sorry to keep you over.